So we had some basics to get out of the way, which include scalar and vector quantities. We spoke about that, right? We said that scalar quantities are quantities that only focuses on size, right? So if we are describing, the trajectory or the movement of a person, we would say that person is moving um the person is moving 10 meters, right? So that person moves 10 meters. Let me get my pen here. 10 meters. But if we focus on a vector quantity, right? If you look at a vector quantity, the vector quantity focuses on both size and direction, not only size, right? It focuses on size and direction, right? So that's what we wanted to accomplish last week. All right, so we now move on to different types of scalar and vector quantities. All right, the main scalar quantity, right, we started with was distance, and we said that it describes the amount of space between two objects. Like right here, we have object A and we have object B. Distance is the amount of space that is between these 2 points, or the amount of ground that is covered by an object when traveling. All right. On the other hand, this places a vector quantity that describes the amount of space between an object in a particular direction. So we now become more specific as it relates to the telling somebody about the displacement. So we said that person travels 10 meters north or 40 meters south, right? So it's basically the amount of ground covered by an object in a particular direction. Are we good here? You can type in the chat, yes sir. Any questions? All right, so I don't hear any questions. So that means that we are good. All right, so we can move on now to describing the movement of objects in a particular direction. So we have the first one, speed, which is a scalar quantity, and it describes how fast an object is moving, right? It describes um the the the, the, the movement of an object. So if an object has a higher speed, it will be able to move faster, or it will be moving faster. On the other hand, velocity is a vector quantity that describes how fast an object is moving in a particular direction. We covered this last week. Um, so we now get more specific as it relates to the direction. So we say an object is moving 10 meters per second in a particular direction, or moving north 10 meters per second. All right, so the distance that the objects move per unit time, that is our velocity in a particular direction. You see the direction coming up back again, right? So what this means, we move over here. We did this, right? So we have velocity here, and we said this is the formula for finding the velocity or the average speed, right? So we need first the total distance covered by the object, right? So say that object is is traveling from this point to this point. All right, let me get more practical in this case. Let me get more practical here. All right, it's not coming out. All right, so this person moves from this point to this point, right? And between these points is 3 kilometers, right? If we convert 3 kilometers, how much do we get?
3,000 meters.
Right. So we convert, thank you, we convert 3 kilometers. 1,000 meters is 1 kilometers, right? So if we do the conversion, we see everyone sees that. Please tell me if everyone sees that. If you're not seeing it, please tell me.
Yes, sir.
All right.
Sir, me see them what your page, me see.
All right, these are just notes that we got. These are in Google Classroom. These are notes from the last class.
But we must remember that last class, so you can stop see that now.
All right, let's move on. Right. So we have our velocity here, and our formula is the total distance covered over time. Right. If we traveled from here to here, right, in say 10 seconds, you would have to divide the 3000 by 10, which would eventually give us about 300, right? So the unit now, we can move on to the unit, which says that V, if V is equal to S over T, what is our unit for the total distance covered?
Meters.
Right, meters. And what is our unit for time?
Seconds.
Seconds. All right, perfect. So um, it would be meters over seconds, right? But we want to put it in a way that is presentable, but this is in the denominator, right? So we would attach this negative one here to the seconds to show that it was in the denominator right here. Are we all seeing that?
Yes, sir.
All right,
Yes, sir.
all right, beautiful. All right, so give me a second. Let me clear this board, all right, and I'll come back. Let me just clear this board because we didn't do acceleration the last class. And so we're going to touch on acceleration. No, we didn't have time to do it last class. And let's bring up back that slide. All right, let's try it again. Should be clear now. All right, so just tell me if you're seeing this. Can type in the chat, yes sir, no sir.
Yes, sir.
Yes, sir.
All right, so we know are going to try and describe acceleration. Now, acceleration is our change in speed, right? So T, we start at the top, acceleration. So when we say a body accelerates, it simply means that it was at a constant velocity and then somehow or with an added force. These are some fundamental things that we need to get out of the way before we actually move to what we want to accomplish today. Right? But for a body, it was at a constant speed and somehow a force was added and it begins to accelerate. So somehow we start to press on the gas, right? We start to gas up the car and the velocity increases. That means that the body accelerates, right? So the V here represents our final velocity and the U here represents our initial velocity, right? I will repost this. Well, the notes are there already, but I will repost this section. Yeah, I will repost this section. And T is our time, of course. All right, so let's do a quick question. Right, our body, our object is car is moving. Um, let me draw this car here quickly. So this car is moving in this direction, right, at 10 meters per second. Remember, we said our units for velocity is meters per second. This is up. This is 10, right? 10 meters per second, and it increases. The person in the car begins to press on the gas, and it increases to 20 meters per second. So it increases to 20 meters per second. So our initial velocity would be what?
10.
20.
So 10 meters per second, right? So that would be u equal to 10. And final velocity would be what?
20.
20, right? 20 meters per second, right? So now, if we rewrite this formula, we bring this formula down here. So A equal, so what would we have here?
10 meters.
Minus 10.
10 meters.
10 or 20? Remember, as
20
go
meters,
first.
sir.
20 minus 10.
20, right? 20 minus 10. Are we all seeing that? All right. Please stop me if you're not seeing that. Thank you. All right. So this happened in 2 seconds. I hear a question.
Sir, can you start over, please?
No problem. So we have our object here, right? This is our object. This is our Lamborghini, right? And we're driving our Lamborghini at 10 meters per second. This, remember, is described velocity, right? Meters per second here. This is our unit, meters per second. So it's original moving at 10 meters per second, but with the person inside of it, increases the velocity to 20 meters per second. So this is now our final velocity, v, but it was initially at 10. So we would have 20, which would be the final, minus 10. All right, and this all happened in 2 seconds. So time will be down here, right? We'll have 2 down here. So what do we get? Are you seeing that now?
Yes, sir.
All right. So what do we have here now?
So is the answer 5?
All right, let's just work through it, right? What we have at the top.
20 minus 10
Minus
equals
10.
All right, over 2. And this will be equal to
5.
all right. So don't just jump to the answers. I appreciate if I see your steps. All right. I want to know that you fully understand what you're writing. All right. Okay, let's move on to the units now. So at the top, we have we have velocity, right? And what is the unit for velocity again?
meters per second.
Meters per second. And then what's the unit at the bottom?
Second.
Seconds.
Seconds, right? So what is our final unit?
5 meters per second.
Meters per second. What?
-1.
We have -1 already, and we're adding 1 more second.
Negative 2.
All right, meters per second, -2. Meters per second, what? Squared, right?
Square.
Right.
Meters per second squared. So our final acceleration for this Lamborghini right here is meters per second squared. Are we all seeing that? Please interrupt me. I would appreciate it.
Yes, sir.
Where me not get where 2 come from.
Or 2, right here.
No, the squared.
Okay,
It took.
I want to try and explain.
Sir, because you have 2 seconds, or because the second, you have 1 second in the numerator and 1 in the denominator. So you square it.
If we not quite, you have to be more specific. If we simplify this down, remember our unit for this was m over s, or unit for velocity is m over s, right? M over s,
So you want to put it in the same.
right? So m over s is our velocity. This side is v, and then we have another seconds coming here. So it would be m over s squared, because these two multiply by each other, right? These two s times s squared. We're not going too deep in this, right? You won't need to show. I just wanted to ensure that we understand the whole process, because you'll be doing this if you're moving over into a higher, say cape. You say you're doing cape, right? And you want to do Medellin doing cape, right? You'll have to be able to work around this a little bit better. But it's very simple, right? Are we seeing this second squared?
Yes, sir, master.
Yeah, and for the person who was having trouble a while ago, are we seeing that?
Yes, sir.
Yeah,
Yes,
I'm not sure the names because the participants, or I should leave that open. I'll put it over here, but I won't even get to see. All right, let me try and decrease the size. All right, it's not gonna work. Yeah, so I'm not seeing who is asking the questions, but I hope you're all good. Please interrupt me if you're not okay. All right. All right, so we'll move on now to Newton's 3 laws of motion, right? And we started to talk about this already from last class, right? And we said that an object at rest will stay at rest, and an object in motion will stay in motion with a uniform velocity unless an external resultant force acts on it, right? We spoke about this already. Anybody remembers?
Sir, if we go back over that, please.
Go back over. All right. Anybody else remembers?
No, sir.
No. All right. No problem. We have our bottle here. Let's say we have a bottle of water here, right? And a bottle of eggnog, yeah. And it's not moving. It's just going to stay there forever. It won't move. So an object at rest will stay at rest. So we accomplished this already. This is correct, right?
Right?
All right. So it will stay at rest. It will not move forever, right? But let's just say a car is driving on a very slippery road, right? It's not like Jamaica's road, right? Let's just say it's like a slippery dirt road, right? And it's wet, so it has little friction. If that car is driving, it will continue to drive at that particular speed, right? It will continue to drive at that particular speed. So it's not under the influence of any other force but friction. Friction is the only thing that's really affecting it, right? So it will not stop. It will continue because it's slippery. There's no friction. But as soon as we apply an external resultant force, let's say we put that car on a Jamaican road, right? It's a little rough, right? So it has more friction. So the fact that it's moving and it has more friction, then you'll find that the car begins to slow because friction would be. So this is our car here. Right, so it's not the best car in the world, right? And let's just say it was on a slippery road. Let's just say that's straight, right? It's straight and it's slippery. No influence of any friction or anything, right? Now, if we it will continue at a constant velocity. It will not stop moving. Do we get that?
Yes, yes.
Yeah, we get that. All right. So now, if we add friction, the car is a little rough, like the roads in JA, right? We have roads in JA now. They are a little rough. They're not as smooth as before. Now, because of this, there will be friction acting in the opposite direction. Friction will cause the car to slow down. So while the car is moving in this direction, you have a resultant force moving in this direction, slowing down the car. We get that?
Yes, sir.
Right. But an object at rest, it will stay at rest until we begin to apply a force. This guy right here. This force here, until we begin to apply that force, it will not move. Do we get
So,
this question?
sir, why it moves in that direction and not the other way?
Friction?
Yes, sir.
All right. So the car is it's under no influence of any force. Let's just say it's moving. Wonder if I can find a simulation on this quickly. There should be a simulation I have here. Right, so the car is moving and it will continue to move. We get that. It will continue to move while it's 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 not under any force. Do we get the that we get that? Do you
Yes,
understand
sir.
that? All right.
Yes, sir.
So it will continue moving, but the friction, on the other hand, it depends on the roughness of that particular object. Depends on the roughness of that particular object. So if the object is more rough, if it has a higher level of roughness, you'll find that it will not move as quickly. So that will mean that the 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 force of friction is being applied in the opposite direction. So we work off that basis. The fact that it's as friction increases, you'll find that the you'll find as friction increases, you'll find that the velocity of the object decreases. Right. So we mainly work off that. But it's nothing too much to really focus on, or you won't be tested or anything. You will just be required to know the first law of motion. Right? All right, so it's not coming up. I guess we'll have to move on.
Sir, so it have more than one law, sir.
Yeah, so this is the first one. It has three laws. Newton. Newton has three laws, right? We'll go to the second. Oh, yes, inertia. So before we move on, so the inertia of an object is the resistance of the object to change its position, right? So if we go back to this bottle here, and it's on a table, you will find that this object will put up a resistance. If we don't put up enough force, for it to move, then the object will move. So we have to apply a force that is greater than the value of the inertia here for the object to move. Are we seeing that?
Yeah, yeah, yeah.
Right. So in order for the object to move, we have to apply a force that is greater than the inertia of the particular object.
External force.
All right, I hear a question.
No, sir. No, sir.
All right, please stop me. Remember, you can stop me if you have a question. All right, so the second law is that force is directly proportional to mass times acceleration. All right, remember this, we spoke about this a while ago, acceleration, and we got a better understanding of what the acceleration is. So force is directly proportional. Remember we spoke about this as well, directly proportional. What does this mean? When two variables are directly proportional, what does this mean again?
Them equal as no.
It means that as one increase, what happens to the other one?
It increases.
Right. So if they were inversely proportional, if one increase, what would happen to the other one if they were inversely proportional?
It would decrease.
Yeah. So it would essentially decrease. So it's just two separate things, right? You see coming up again, right? You'll see that um those two characteristics coming up again. All right, so force, we're now describing force because Newton found that he found the importance of force, and that if you look at this quickly, what is the velocity, the initial velocity of this object right here, our bottle of eggnog? What is the velocity here? Is it moving?
No.
So what is the velocity?
Zero.
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 So in this case, v is equal, or no, u, right? Let me just rub that out. U. You
Why
remember
you,
u is
sir?
the initial velocity? Your question? All right. Okay, so u is equal to 0. Now, if we start to move the object in this direction and say our v increases to 5, we realize that there's a change in what? In velocity. Right, in velocity. So that means that it's an acceleration. So we need a particular force in order to get acceleration. That's simply what it's trying to say. So in order for us to get acceleration, we need a force. We cannot get acceleration without a force. And the unit for force is Newton, of course, named after the person who came up with the idea. You'll find this coming up more in physics, right? The persons who come up with the theory, they get their names on the particular units. So are we okay here?
Yes.
All right. So this essentially means that 1 Newton is describing the force is the amount of force that is required to move 1 kilogram of an object with an acceleration of meters per second. And we see this coming up again, meters per second, unit for acceleration, right? So are we good? Are we okay?
Yes, sir.
All right. Now, as you said, F equal ma. Now, what is the unit for m? What do we usually use for m?
Mass, sir.
Yeah, m is the mass, right? What is our unit?
Kilogram.
Right. So kilogram goes here, and our unit for acceleration is
Meters squared.
right. The meters per second squared. Remember that negative means per. All right. So kilograms is meters per second squared. Our unit then is mass, acceleration, kilogram per unit squared. So this is equal to newtons, right? Whenever we see this right here is our unit for force is equal to newtons. Please tell me if you have a question. If you're not understanding, all right. Okay, that is a yes, we're good. All right, now we can move on to linear momentum. Finally, we're here, right? I'll erase the board, right? But we can just go through it. We have less than a minute on this particular meeting. All right, so linear momentum is the term in physics that is used to describe an object with a mass in motion, right? So we found it difficult to just be able to describe the velocity. So we say an object is moving, say from moving north at 10 meters per second. We are missing out something here. We are missing out how big is that object. We want to describe everything about that object. So that's where momentum comes in. It is used to describe an object with a mass m in motion. So linear momentum is considered a vector quantity. Why? Why is this the case?
So it looks at the size and direction too.
Size and direction. But what in the formula comes with size and direction?
Velocity.
Right. So velocity looks on the size of the direction, right? The size of the speed, right? The magnitude, and it also focuses on momentum. And it also focuses on direction. Sorry. So if an object is moving 10 meters per second, 10 meters per second north, right? This is the size of the speed of the object and also the direction, right? So because velocity is a vector quantity, momentum is also a vector quantity. We'll do this exercise when we come back. We'll pause and